Chapter 1 Number System. Upon completion of this chapter, readers should be able to define and state the rules of indices, surd, and logarithms, carry out the algebraic operations of indices, surd, and logarithms, and solve equations involving indices, surd, and logarithm. Let us do some reviews on number system. Let us look at sets. When we want to treat a collection of similar but distinct objects as a whole, we use the idea of set. For example, the set of single-digit numbers, which consist of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, can be written as this, where the symbol D denotes the set and the braces are used to enclose the element in the set. This method is called roster method. Another method is to write like this, which is called set builder notation. This statement is read as D is a set of all x such that x is a digit. It is helpful to classify the various kinds of numbers that we deal with as sets. The biggest family of numbers, which include all the numbers that we consider real, is called set of real numbers. And then inside these real numbers, we have irrational numbers. And then we have rational numbers. And inside rational numbers, we have integers. And inside integers, we have whole numbers. And inside whole numbers, we have counting numbers or natural numbers. Natural numbers are numbers starting from 1 to 3 onwards. And whole numbers that numbers starting from 0, 1, 2, 3 onwards. Let us look at in detail the characteristic of each classification of numbers. Let us look at rational numbers denoted as Q. Rational numbers are numbers that can be expressed as fraction of two integers, such as a over b. And as we know it, b, the denominator, cannot be 0. Examples of rational numbers are 3 over 4, 5 over 2, 0 over 4, negative 2 over 3, and 3 over 11, and so forth. The set of integers is a subset of the set of rational numbers, because integer a can be written as a over 1. Rational numbers may be represented as decimal. For example, the rational numbers 3 over 4, 5 over 2, negative 2 over 3, and 3 over 11 may be represented as 0.75, 2.5, negative 0.666 onwards, and 0.272727 onwards. The decimal representation may terminate or ends, and if the decimal representation neither terminates nor ends, it will exhibit a pattern of repetition. Let us now look at irrational numbers with the symbol Q prime or Q bar. Irrational numbers are numbers that cannot be written in the form of a fraction a over b, represented by decimal that neither repeats nor terminates. Several examples of irrational numbers are square root of 2, which is equals to 1.41421356, and the decimal will go on and on and on. The number pi and Euler's number e. As we can see here, the decimal form of it neither terminates nor exhibit a clear pattern. Now we know about real numbers, but is there any number that is not real? Consider x squared equals to negative 1. There won't be any real number that could satisfy this equation. This equation will give us x equals to plus minus square root of negative 1, which we know does not exist. Therefore, we call this number an imaginary number. Imaginary number I is equals to square root of negative 1. Therefore, square root of negative 3 is equals to square root of 3i. Square root of negative 9 is equals to 3i. And negative square root of negative 7 is equals to negative square root of 7i. When we combine a real number and an imaginary number together, we call this number a complex number, and it is in the form of a plus bi, where a and b are real numbers. A is called the real part of the complex number a plus bi, and the real number b is called the imaginary part of the complex number a plus bi. In other words, the complex number is addition of a real number and an imaginary number.